I'm Charles Walker. I have the pleasure of introducing Chris Bosse. And I didn't prepare anything, so I deliberately decided to do this very informally. And I'm not going to give you any real factual information about Chris. I think he'll present his work, and that in itself is introduction enough. But I do want to just talk a little bit about the way Chris is positioned in kind of architectural culture at the moment, because I think there is something quite relevant to say there. Most of you guys are studying and you don't have that much experience in practice. I think to some extent practice is changing. And maybe, and well, I quite hope, but possibly we're moving out of a period when, what I would characterize as potentially like the atelier period of architecture, when, an atelier being like the master of the atelier, and a plethora of minions who are part of the production machine that delivers that person's vision. And I think a little bit we're moving into a period now which might be, I'll use the term very loosely, but it might be almost considered nomad architecture. It's a movement away from a traditional and very classical structure of the client, the architect, the sub-consultants, and the production and the delivery of the building done completely in-house, towards a much looser, almost network organization of a number of different experts brought together on a project-by-project basis. And I can only illustrate like Chris's kind of, or my impression of Chris in that context by describing a bit our personal experience. Like, we worked a bit together when he was living in Germany, and then he moved to Australia, and then, through certain influences, some of them being like the kind of, to some extent, like the kind of movement of ideas globally through almost architectural information systems, publications, schools, critiques, dialogue, exchanging emails, sketches, keeping each other informed with the projects that one is currently working on. And through this kind of form of very loose, informal communication, maintaining a contact. And I think in that way I'd almost describe Chris a bit like a nomad. He works he's employed at PTW Architects, which is a very large Australian practice. But he's constantly traveling the world, passing through London, and whenever that occasion happens, we maintain loose contact, critiquing students and so forth. And so I think now what is kind of emerging is, rather than a kind of atelier type environment, you have a loose network of a number of designers who are moving around the world and communicating with each other and exchanging ideas. And it's in this kind of rich mix, almost like a soup, that from time to time something strikes and a project is realized. And Chris had the great experience of that occurring at a really significant and international scale. So I hope, I'm quite optimistic about that future, where that process continues, that in a way the production and delivery of architecture changes from very traditional corporate structures to a kind of much looser network relationship where different creative people can come together on a project-by-project basis. I think that's very much my experience of my relationship with Chris, and I'm quite optimistic about that future. But he needs to present his work, and you guys have a look, yeah? Chris.
Thank you very much. Thank you for this introduction. I think it very much captures a lot of things that I'm going to talk about. Is it possible to dim the lights a little bit? First aspect is definitely collaboration. Me being inside a large-scale practice, collaborating with some of the best engineers, architects around the world. In the particular project that I'm going to present, collaborating with the Chinese Design Institute. Chinese design institutes are the formerly state-owned design firms that now are transformed into private practices, and every foreign architect has to collaborate on every public project with one of these firms, and that's a great challenge, and it's a great advantage as it turned out. So this is a recent photo of PDW. This is just us in Sydney, 150 architects currently, working in 7 offices worldwide. And this is a very brief introduction about my personal background. I had originally a very classical education in architecture in Germany. My final project was about Andrea Palladio and his relation to time and space. And afterwards, I moved on to a master's in Stuttgart University, where I was confronted with new concepts of architecture. One was the concept of the digital. That was in the 90s, and the first wave of digital architecture was very much about creating shapes and creating pixels that moved in space. And not every single one of these pixels necessarily needed to make sense. My project was about virtual realities, representing real space in virtual space, creating environments in VR caves, where with goggles and data gloves you move through spaces, but they're not real. There's no gravity, there's no environment, but there's perception. You can see these spaces, but you can't feel them, but you're in them. The second concept was the concept of form finding at the Institute of Lightweight Structures by Professor Frei Otto. So Frei Otto at the time said he's not designing, he's finding shapes. He sees himself as a researcher, and he investigates shapes in nature or structures in nature, and finding optimum configurations of structures rather than designing them the way you want them to look and then figuring out how they stand up. One of the most prominent examples is the Munich 1972 stadium, which is entirely based on the surface tension of soap films, and therefore still till today one of the lightest and most filigrane structures in the world. So hence my interest in sort of complex systems in nature and their possible applications in architecture, and whatever these applications may be, if they're spatial, conceptual, programmatically, or as an application of ornament. As Charles introduced me, in 2002 I worked for a German firm called SMO Architecture, and we participated in a competition in Berlin. One of our students had Charles as a teacher at, I think, at the Stedel School in Frankfurt, and she suggested to work with the Advanced Geometry Unit in London. So we came here in 2002 and had a workshop. The ideas behind the concept were that the perception of current architecture being a pure repetition of floor plans that is then retro-clad almost, and facade is nothing more than a cladding of a highly efficient structure that is sort of a given almost by a developer. While originally structure and appearance was going hand in hand, the cathedrals, every element of architecture is at the same time an element of structure, and every element of structure has an architectural expression. Later, Paxton Crystal Palace and other projects are examples how this structure turns into the architectural experience and becomes inseparable. And often these structures are learned from nature. Buckminster Fuller, another person in that field, who built this pavilion in Montreal, I think 1968, where you can't really tell what is structure and what is architecture. It's a unity. And at the same time, Frei Otto building the Montreal pavilion, which was later leading to the Munich stadium based on surface tension. And at the same time, Frei Otto wrote this book by the name of Seifenblasen, Forming Bubbles, and we'll see later how this book comes to relevance. The idea, so for the high-rise tower, and this was basically what we came to London with, was we wanted a structure that at the same time is architecture, a structure that represents nature, natural systems, organisms, and that is not just an extruded floor plate cladded with a funky facade. And after one day workshop, we had these sketches and the word packing. So packing meant for us, we put spheres in a box and shake the box, and all the spheres would self-organize themselves, so they leave the minimal amount of space in between them. So you have some sort of structural package, although highly undetermined or underdetermined. When we then slice through this structure, or through this undetermined accumulation of spheres, we would get a slice of somehow a determined structure that we would wrap around the building, so the structure and the facade becomes the same element. At the time, we weren't 100% able geometrically to resolve this problem. And what we did was simply modeling the bubbles, the spheres in max, and subtracting them from the volume. About the detail, we had a very blurry idea at the time, and it actually stayed at that level of resolution. But we had a high-rise building that looked highly unusual and looked different from anything else we had ever seen. Within Charles' advanced geometry group, I think everybody knew we were onto something, but nobody knew what it was. And there was a certain excitement about this project. The only person not excited was the developer, who decided not to go ahead with it. And the last thing we heard was this page faxed to us from Charles, which was a copy from the Frei Otto book, that somehow talked about these rings or these spheres under compression turning into some sort of three-dimensional structure or foam or hexagons. I moved on to Sydney in the same year, in the autumn, and joined a large-scale architecture practice called PTW Architect. This photo is relevant because PTW Architects has actually built half of these buildings, apart from the Opera House. They are one of the biggest firms around for 120 years. And you can imagine over the arc of 120 years, a lot of people go through this office, and a lot of different styles and qualities come out of this office. And as remote as Australia sometimes seems from this side of the world, it is actually quite close to a lot of places. While Australia has 20 million inhabitants, it also has 20 million border movements every year. So statistically, every Australian leaves the country once a year. While in America, for example, I think the percentage of travel documents is something below 15%. So we were invited to join an international competition against some of the biggest firms in the world for the National Swimming Center for the Olympic Games in Beijing 2008. The site is in the center of a north-south axis that takes you from the Forbidden City to the north, which is now the Olympic Park. And you see on this image already, again the team, you see the stadium, the main stadium, by Herzog de Meuron, which was a competition that has just been decided at the stage. So we knew what our neighbor was, which is highly unusual for competitions like that. It was almost like designing in an existing condition. So we had a big circular building called the Bird Nest, and somehow it was painted red on the inside and symbolized fire. This image before I wanted to show, on the top right side, there's the Chinese team from CSCC from Beijing who joined us for the competition in Sydney for a period of 10 weeks. And the Chinese partners had actually a very big impact, as well as later the structural engineers, in the design process, in tackling the challenge of building an Olympic project, building it in China, in the heart of the city, and next to an existing main stadium. So, reading the symbolism of the main stadium as a big ring of fire, which in Chinese philosophy stands for yang, you need an opposite, a complementary element, which is the yin, and in this case water, and a feminine counterpart. So we decided on a blue building that interacts with the red building, and we decided on a square shape, and we decided on water as somehow a theme of the building, which is quite obvious, building an aquatic center. The square shape is the primal shape in Chinese architecture. The Forbidden City is square. The Summer Palace has a lot of square buildings. The Temple of Heaven is square. And the history of Chinese architecture goes back thousands of years, obviously. There's a strong linkage to the man standing in the middle of a square with equidistance to all sides and so on. So there was a strong reason for this shape, and it also made a lot of sense putting a square next to a circle. We had a blue box and a red circle, yin and yang. So the spirits were happy already, but we had no idea what to do with it. We looked at, again, at nature for inspiration, and this time we looked more into water, elements of water, corals, bubbles, foam, and sort of more specific into what could be relevant for our building. Again, creating a building that is not structure plus facade, but structure and facade in one. So we applied the system that we had previously found, and we found that it seemed to be something that made sense as a block of foam, somehow representing water. Now, as much as the computer liberates us from having to be able to draw everything, it also limits us to what you can draw on this particular program or with this particular computer. This drawing here is a 2D drawing, represents some form of foam, but it doesn't represent foam because foam is three-dimensional. This drawing is two-dimensional. So it basically reads as an array of circles. Remembering the facts out of the Frei Otto book, we were on the hint to look more into foam. So we mapped the foam onto the building, and all of a sudden we had something more three-dimensional that would fully represent water for us in a build form. It's almost like a block of water. That's seemingly a contradiction. Looking closer into the geometry and structure of foam, something that many people have done in the past, you find on Google actually that there are certain theories about geometry of foam. One of the oldest, dating back to 1873, that finds that all the angles between three adjoining bubbles are 109.4 degrees, and they all join at the same degree. The latest foam theory was then found on an Irish website by two Irish professors, Professor Weir and Phelan. And they state that if you mix 12-sided polygons and 14-sided polygons, three-dimensionally in space, and array them endlessly, you would have a structure that doesn't leave any spaces in between. While our bubble model with the chewing gums earlier left all these spaces in between, now we have a highly defined package with no spaces in between. And a package that has very limited number of different edges and nodes. So as a principle of how the structure then derives from that, we have two different geometries that array in a cluster of 6. They array three-dimensionally into a large amount of foam, theoretical foam, theoretical physics foam, that we then slice into the volume that we want to achieve, the volume that was determined by site conditions, program, and so on. And from the first data model, from the first three-dimensional computer model, which was so much more sophisticated than our early 3D Max model, we managed to get a physical model built with the process that is referred to as stereo lithography. I think that's nowadays quite a common tool. You probably have one in the school here too, where you have some sort of resin or powder which is hit by 2 laser beams, and where the laser beams hit, the material becomes solid. So any three-dimensional geometry, if you're able to determine it in the computer, you can build it. And that then arrayed to the entire building, which is 200 by 200 meters and 35 meters high. We have 22,000 elements and 12,000 nodes. And despite the high degree of repetition, when you look at the original images of microscopic foam, there's such a strong similarity that it still surprised us. So this geometry apparently is the most common geometry that you find in nature, that you find in little animals, that you find in foam, that you find in coral reefs, and that you even find in the nose of my dog. This block of foam then, 200 meters, 35 meter high, is excavated to accommodate the spaces. An Olympic pool, this is the biggest Olympic pool in the world, accommodates a diving pool, a 50-meter pool, warm-up pools, a leisure center, and an ice rink. And all these spaces are literally carved out of the geometry. But they could be in any shape. You could carve out any shape of this geometry, and in theory the geometry would still be stable, because it's fully three-dimensional, and you could put the entire building on the side. It's a non-directional structural system, which proved to be extremely efficient for Beijing, which has seismic conditions, earthquake. So here you see another sectional model where you see spaces carved out of the structure, and the space on the right we refer to as the bubble bar, which is the restaurant and a sort of VIP bar that sits above the entry. To the left you see 2 spectator ranks with 17,000 seats and the diving tower. Talking about models in China nowadays, you have incredible industries of model making, 3D model making as well as physical model making. And these guys in Beijing have now specialized in building Watercube models, and they literally build Watercube models and bird nest models on a daily basis. You have these 10 guys, and it's like an assembly belt. Everybody has this fixed role, and they know exactly what they're doing. So you can ring them up and get a model built. While we previously thought nobody would ever be able to build a model like that, they have now figured out from our 3D computer geometry to build it in reality, which is a big step, because if you can build a model, it's more likely that you can build the real building as well. This is one of the facade impressions, or the external impressions, where you see the structure and the facade becoming the same element, and the structure shining through, and sort of a layering. And that is something that we wanted to achieve, and we wanted to learn from water as well, this effect of layer, that the eye doesn't know where to stop. It sort of has an endless depth. And an internal impression of being underwater or under a block of foam, sort of an ephemeral view. As Charles mentioned earlier, the Eden Center in Cornwall was a project that was built, I think, 10 years earlier, which uses a facade technology that derived from space industry, whereby inflated plastic pillows are used instead of glass. And these plastic pillows can span up to 9 meters, and they weigh only 1% of the weight of a comparable glass structure. It's highly transparent, highly UV resistant, and it's practically undegradable material. The next project of my knowledge is the Allianz Arena in Munich that has come to fame last year in the World Cup. So basically it's really a thin film of plastic. It's 0.1 millimeters thick, and you can't imagine that something like that can carry any load, but it's extremely strong, extremely transparent, and extremely undegradable. So NASA invented it originally to shield satellites. And so the system works that the foam structure is the internal structure that on both sides is wrapped with this lightweight material. The solar energy is captured in between and can be used to heat pools and interiors. So you create like a greenhouse environment that is highly energy efficient. And you have a daylight situation. Usually pools are just black boxes, and then on the inside you have to spend a lot of electricity and money to light them again. This is how the system works with clamps. And so that was our competition entry for the National Swimming Center, sitting next to the bird nest. And out of the 10 entries, it was first shortlisted to 3 entries that were on public exhibition. And with an overwhelming majority, the public voted for our building, which was obviously a strong, very, very nice compliment for us, and a very strong argument that the population accepted the building in its simplicity and yet being so different. It just seemed that these two buildings work together so well that now people say that the bird nest got its justification sort of afterwards by adding the Watercube. It's almost like there was something missing before. The entire geometry, the 22,000 nodes, 22,000 beams and 9,000 nodes, or what it was, are based on a 3D geometry, which is a single line model, a single line AutoCAD model, which is only 1 megabyte big, and you can send around to all the engineers and other people involved, and that describes to 100% the structure. So from there on, every necessary information can be extracted from that model, and our partners from Arup in Australia, and I believe with the help of Arup London, have developed an automated system whereby every single beam and node can be described in this numeric model, can be calculated, can be weighed, can be costed, and can be sent straight to the steel manufacturer from where it gets to site. And that's probably what 30 years ago, when Fry Otto was playing around with the same ideas, wasn't available, where you would have to build physically every single member and somehow stress test it to be sure what it's sized. All these elements have different dimensions, and the big advantage is that they carry only the load that they have to carry. While traditionally you would size the biggest member and then all the steel members have the same size, it's a big waste of steel and the structure gets very heavy. While here, the members carry only the load that they have to, and you have a very efficient structure saving steel. All the necessary information, elevations, anything you need, cutting patterns, can be derived from this model, and the details are all resolved 3-dimensionally within this model. For the interiors, again, we were inspired by water and bubbles and randomness and transparency and reflection. and that became an ongoing theme throughout the building. The idea of seeing something glowing within the building at night, the idea of painting the structure with a fluorescent paint that glows at night, and the idea of having reflections like the surface of a lake, something undetermined, not a light here, light there on a grid, light that moves around the building. Doesn't run very smoothly here, but with these buildings or with this material, it's probably very difficult. Light is always very difficult to simulate, but in particular, if you have all these different layers of the structure, all these layers of plastic material that absorb the light differently, it's almost impossible to really predict the final outcome. This was one of the attempts. And using LED technology, you can achieve any color you want. And with great power comes great responsibility, because 3 of these colors obviously we don't want, and we have to somehow avoid that someone ever switches the yellow on. The interior is only briefly the concept of randomness and sort of softness and blueness goes through the interiors, with all the corners being rounded. Random light circles. To our big surprise, in 2004 we were invited to the Venice Biennale, and when we arrived there we got awarded the award for the best project in our category, which was previously unheard of for an Australian company. And soon after, the project got into construction. So again, working in China makes things different. In China, you don't prefabricate a lot of things. You make up for it with a lot of manpower. So on the first day of construction, the groundbreaking ceremony, 2,000 site workers showed up, and these 2,000 people would keep going for the next 2 years building this building with great pride. Starting with a big excavation. Again, it's 200 by 200 meters, and these are just a few impressions of how many people are involved and what they do. And at the same time, always trying to maintain the initial ideas. The facades, we did a lot of samples. Because it's so hard to visualize it in the computer, you need to build prototypes, and you need to test the light, you need to see how the reflections work, you need to see how it reacts to illumination. These silver dots that you see, they're solar protection, because the material lets so much UV light through that you have to keep it out to an extent. So there are different densities of silver fritting. This prototype is in scale 1 to 2, so in reality it's twice as big. The color was a big question too. Color, we drew it always as a blue building, but we thought like blue as in the sky is blue. These people made it actually a blue ETFE, and it was way too blue for us. And so we asked them to revise them and come up with more prototypes and different colors and different transparencies. A lot of testing involved, because there's so many layers of ETFE, you have to put them all together and really see what they do in combination. And this was the final prototype, which came pretty close to our ideas of transparency, translucency, and the shadow casting, shadow playing on the different layers. And now it comes to the structure. And when I said there's not a lot of prefabrication, obviously every single steel element was prefabricated, but individually. We always thought that they would build entire parts of the building in big workshops and then helicopter them on site and drop them on site, because it's so highly complex geometrically. But what they did was building every single element, and every single element that came out of the three-dimensional model that was sent to the steel manufacturer. These are the nodes. And then was literally side welded by 400 specially trained site welders. The simplicity of this construction is almost undescribable, but in some way there's a strange mix between totally high-tech, you have this highly sophisticated 3D model, you have everything set up, and then you have bamboo scaffolding and a few people carrying the nodes around. So it's what we refer to as Midtech. It's using high-tech and low-tech at the same time and somewhere meets in the middle. To give you an idea of scale, there are 2 people climbing on one of the bubbles. They are 7 to 9 meters in diameter. Those were the first bubbles mounted on the facade, 500 square meter model, mock-up. And these guys are in charge of how many bubbles are applied already and where the next 500 come from. So again, very analog process. And wheelbarrows, and lifting the nodes in position and welding them on. Interestingly, because you work with a 3-dimensional model that is so highly determined, you don't build up inaccuracies, because every single node is positioned exactly. Then even if you get one node a few millimeters wrong, the next node will be positioned exactly again. So it's not like you start at one end and then by the end you come to the other end, you're 1 meter off. These are the first interior impressions where it started to show how the shadow casting and this sort of surreal interior seem to work. This is the view from the bird nest, and you see here the bubble bar on the left, what I was describing earlier. The area which has a lot more structure and where the space is actually inhabiting the structure. Yeah, these were the photos of sort of 6 months to 8 months ago. I want to quickly show you a few other projects before I show the latest photos that were taken 2 weeks ago. We were very happy to see the project showing up on Google Earth for the first time, but that is somewhere halfway through construction last year. So as a spin-off from this large-scale big project, we have initiated a series of smaller scale projects that are of more experimental nature, or of similar experimental nature probably, but of a much smaller scale. They are temporary pavilions that are transportable, that can be carried in a bag and built up within a very short time in a venue. This animation shows a pavilion that was built for Moet Chandon for a race course VIP lounge at the Melbourne Cup last year. So again, starting with 3-dimensional modeling and a 3-dimensional description of the geometry. The geometry is then broken down into individual pieces with a cell-making software, a stress analysis that comes from cell-making, and then you have this pattern. And this pattern, nobody would believe that you can put it back together and it makes any sense. But the computer calculates how to break down all these double curves, including the stretch of the material, to seamlessly put them back together. The space was only 10 by 10 meters, and the daylight naturally filtered through the ceiling and left these spots, casted these shadows of spots. The funny hats, by the way, I think you have this tradition in England as well, to wear these hats for horse races. So there was like an interesting contrast of this cyberspace interior and this sort of last century headwear. The spots were an interesting way of creating patterns, as they were created by the sun, and when the sun was there they casted spots. When the sun went away, when a cloud came on, the spots disappeared, so the whole building was constantly moving and reconfiguring. So after having studied Palladio, where all the proportions are following certain rules, and all the dimensions are fixed. The question is, if you do these sort of projects, what are your parameters and how do you make your decisions all of a sudden? These sort of buildings look different from every single angle. There is not even an elevation. You can't draw an elevation of something that is so three-dimensional because it doesn't give you any information. You have to look at it three-dimensionally. And I guess that different to the blobs that I was talking about in the beginning, now decision-making can be based on material efficiency, for example, like in Frei Otto's early soap bubble experiments, can be based on advanced computing where individual parts of fractals are put back together and achieve an economy of material, economy of means, spanning large structures, weighing less, packing this space into a small bag, transporting it to space, and it adapts to the space. And the sort of different levels of scales of having the total and then breaking it down into different cells and different fractals that are a fraction of the whole.
What's the material you're using there?
The material is a fabric, which is a nylon derivative. And so the material stretches. And for this particular project, we filled 500 cubic meters of space with 17 kilograms of material, which is with any other material unheard of. So the idea is, I guess, if these geometries found in nature are somehow efficient, and if you can build pavilions with them, if you can build furniture with them, if you can build a table or a chair with them, if you can build large-scale structures that are lightweight, that span far, that are highly transparent, that are transportable, can you apply these to larger projects? Can you apply these systems to a city, to urbanism? Can you use environmental principles that are learned from nature that improve our environment on an urban scale? I believe that the new generation of digital architecture, which distinguishes itself from the first generation of the blob making, of the shape making, of the sort of effect making, the new generation is based on geometry, is based on repetition, is based on systems, and it's based on intelligence that you can feed into the computer to have a more intelligent outcome, and not only an outcome that you like for this or that reason. The Aquatic Center, I guess, shows quite well how a structure that is so unusual and so attractive, at the same time is so efficient, uses 1/3 of a traditional stadium structure, uses 1/10 of the facade material, spans 120-meter column free, and becomes such an architectural icon, not only by the hand of a designer who wants it to be like that, but by many, many reasons that lead to that result. So, talking about computers and talking about parametrics and so on, I don't think that the computer can liberate us from the decision making. I think we still have to be the designers at the end of the day who make the call. But it gives us more transparency in that transition making. It gives us the criteria of making decisions. If you have the Aquatic Center roof with 16 different bubbles on 4 different layers and 12 different transparencies for every bubble, you have thousands of different possibilities, and it's impossible to make a decision just based on your taste or your intelligence. The computer gives you an array of possible solutions from which you can then choose the one that you like best. And that comes down to architectural education, and that's why I'm very pleased to be here at the AA tonight. And what Charles said earlier, some of the projects that you guys work on here, they look out of control. But in all these projects, there's always a little truth that can lead to a fantastic project in the future. And sometimes it seems like playing around, but playing around is an essential part of doing architecture, of experimenting, of designing. And I want to only encourage that, and I'm always pleased to come here and see the reviews. A few last pictures. The entire building is now clad. In comparison, you see the Herzog de Meuron bird nest, which has 10 times more structure than the Aquatic Center. It's still a fantastic building, but it's not based on efficiency of structure, it's based on an effect of structure. So you can see it's the big black building in the back. These facade pillows have really proven to be so versatile on different lighting conditions. Sometimes they look very flat, sometimes they look very bubbly, sometimes they're transparent, and sometimes they look like aluminium panels. You really only understand the building when you see people and a scale in comparison. And it's incredible seeing these sort of unsophisticated building methods leading to such a high-tech result. The whole building, by the way, was built for $100 million US, which is the equivalent of the Prada shop in Tokyo, for example. So I believe in the future cost is sort of a different issue too. There will always be the highly luxurious, fantastic projects that can afford to spend a lot of money for high-tech brands, but there's also architecture that has to be affordable, that has to be built with normal means, normal technologies, but smart technologies. The interiors are currently in this state. We are promised that the building is finished in 6 months. We have a few doubts about that, but having seen the 2,000 people on site, they probably will finish in 6 months. The scaffold here is another sign of sort of low tech. The entire building is scaffolded. The entire box was built in a scaffold before the building was built, and the scaffold actually was heavier than the steel structure of the building and more expensive. This is the roof, and again, sort of scale. There are these gantries and roof gutters for maintenance. The big bird nest is nearing completion as well. And we got this photo sent from Herzog de Meuron, so they don't seem to be that unhappy with their neighbor. It certainly has a lot of public attention. On that weekend, I was there in December last year. It was on 4 out of 5 newspapers of the national newspapers in Beijing. And this was the photo of the last bubble being installed on the roof, and that was the reason why it was on the press. It's every time something happens in the Olympics, it's big national news. And I think this is the last photo, and I want to thank you very much for your attention, and to have a drink. Are there any questions?
Yeah. Okay, thanks very much, Chris. I think we have time for a few questions, if anyone wants to start out. Yeah? Sure.
I think it was 2 months ago that Klaus Osterhuis was lecturing here. Is it on? It was 2 months ago when Klaus Osterhuis was lecturing here, and one of his issues was building without scaffolding. Mm-hmm. Like as a puzzle system, that the whole thing is, it's expensive, but it will be low costing because of this fact. Is it an issue for you?
It's certainly an interesting point. It's probably the other way around. Yeah, it's again probably in different countries and different situations you would choose different means of construction. And we were surprised how this building was built, and that it was built to this standard with these sort of simple means and very low budget. But it was built, and it looks actually better than we have imagined and better than we could even visualize it on the renderings. But if there was a way of building this piece by piece without scaffold, we would next time do it, I'm sure. Chris Bosse is interesting as an architect because he said he dramatically changed his entire view on architecture after meeting Fry Otto something like 10 years ago. And he is working on sort of physical form finding merged with digital form finding. So he would play with all these experiments like having woolen threads and dip them into water and see how they all interconnect. Then he would try to do the same thing on the computer and compare the differences and similarities. And I think it's a very interesting way of reinventing things that have been talked about 30 years ago. I guess when we talk about this project as well, like at the end of the day, who's the designer of this project? And there are probably more designers of this project as Elvis Presley impersonators. It's everybody has some sort of contribution, and Charles standing here had a big contribution when we did the bubble high-rise, without which it would never have happened either. And without the Fry Otto book, it wouldn't have happened either. And the only reason that I went to this meeting in London 3 years ago was because my boss at the time couldn't get a visa in time. So maybe if he had gone, it would have been a different building altogether. So that's what I liked about your introduction, I guess, that now we are moving within a universe of architecture, and the ideas are within this universe, and it's up to every single one to take out of this universe what he wants and interpret it in his own fashion. Long answer for a short question.
Yeah.
Hello. I would like to ask some more technical question. I realize, as a continuum of what you said about the many designers, I realized that at one point you ended up with the topology of the overall structure, and then you had the finite element analysis or something from the civil engineers. How many times did that back and forth procedure take place, like the topology, and how did you end up with the length of the elements and the overall size of the bubbles,
Yeah.
and if any tropism occurred on the building, different sizes?
Well, the answer is that only because of computer technology that wasn't available even 2 years before the competition, we were able, within the competition time, to arrive at a state of resolution that we could be confident that this could be built. And in the following 10 months, we had to document the entire building. And within that process, because the process was automated, when we shrunk the bubbles from 9 meter to 7 meter, within a few minutes or hours, the whole building could be readjusted and recalculated, and the steel length and steel weight and so on could be compared. So we could go through this process, look at the results of 5 different variations, and then make a decision based on what we liked, how much steel was used, how stable it is, and whatever other conditions there are. And that is something that without computers would be impossible.
Thank you.
Yeah.
Using a highly regularized structure, you have the ability to turn corners in many different ways. And I'm wondering what made you choose to use the long linear elements to constitute the box. Was that just a design decision to hold on to the box, or did you need that structure?
The long linear sort of frame.
Right, the frame that holds up.
Yeah.
It makes it appear almost as a secondary structure, in a way.
Yeah. I guess at some stage of the process, we try to eliminate any sort of visual structure, any sort of straight line. But at the same time, the building lives from this contrast of total irregularity. Like, look at this form, and then it's confined in a cylinder. And our form is confined in a box. So, in a way, there was an attempt to blur the edges and just make it something of form, but then it becomes a blob again. And we wanted to clearly show that man and nature have met here and the form has been cut. And that's an interesting experiment when you do that with form in your bathtub at home, seeing what sort of shapes you can generate it, and depending on the density of form and so on.
Maybe I'll ask you a question. Yeah.
Yeah.
Well, the one, I mean, there's a lot of things I could ask, but the one kind of statement you put there quite strongly, which I think is provocative and interesting, is geometry is the new blob. Yeah. I mean, I understand. I don't know, a kind of open question. I wonder if you could elaborate on that. Like, I understand the principle. Like, it's no doubt that when we first got access to these small machines and we, all those tools came over from computer gaming and animation, that we could start modeling anything we liked. And to some extent, I think the early generation that took that up possibly lacked rigor in what they produced. But maybe that's just a lead into. Could you take it? Could you elaborate on that from there, Chris? I don't know.
Well, the question for us was, and I think to an extent in your practice, what you are doing, is it legitimate to design anything you like and then make it work because you can, and you probably can, and there are people who do it, and it takes a lot of time, a lot of manpower, and a lot of material, and you have created a shape that you like, but then someone else comes and says, well, I don't like it. So I think that architecture has to be more than just a personal, intuitive thing. If you have two reasons for a shape, because you like it and it's extremely material efficient and saves energy, that's two reasons. If you have three reasons and if you have 5 reasons, then it makes a lot more sense. And you can probably, starting from the other end, starting with an element that you know is reasonable, and you can array and you can play around with and you can generate something with, you can probably achieve more interesting results and more unexpected results than just starting with something that the computer, that you can just distort a sphere in 3D Studio and you like the shape that emerges. So I like the idea that today you can build in intelligence in your design process rather than retro-engineering any possible shape. And this sort of minimal surfaces, the fabric structures, that's a very straightforward line of thinking, because the fabric automatically assumes the minimal state of energy and the optimum shape for a given condition. But there are certainly many other forms and shapes and methods and materials that can be explored in the future.
I'm just wondering what other research your office is doing now that you've sort of completed a few different stages. You've sort of taken this from a large scale to a facade and structure and then to a pavilion. I'm just wondering sort of what you're doing. Are you still continuing with the research at the sub-level, or are you?
Well, when you talk about the office, as you've seen earlier, the office does a lot of things, and there are parts of the office who are interested in this research, and I'm personally very interested in it, and I can see from traveling around the world that a lot of people worldwide are working on similar issues. And that's why I like connecting with these people and talking to Charles every time I come here, and going to Columbia University when I'm in New York. For me, it's one interesting line of research, but it's certainly not the only one. I think there are so many, many more.
You talked a little bit more about systems. I mean,
About?
you talked a bit about how you think geometry today is in kind of response to your, you're talking about repetition and systems, and I'm just wondering, and maybe I'm not being clear, but how you see this maybe translating into another level of architecture. I don't know. I mean, from pavilions, knife done pavilions. Is there another sort of? Do you see it going?
Well, I think there are two directions of scale you can go into. You can go into furniture and into jewelry, what Frank Gehry has recently done. But the more interesting part is probably to go into urbanism and into sort of more universal topics. If you can create an inhabitable unit with the least amount of material and energy, you can probably resolve a lot of problems of developing countries, for example, and that's probably more interesting. And if you then, I mean, you guys do things here like parametric urbanism. I think Patrick Schumacher talked last week. Using the computer to emulate naturally grown cities, sort of looking at the patterns of how Rome has grown over the centuries, what's good and bad about it, and hopefully taking the good out of it and not the bad, and programming it into the computer, and creating cities based on parameters that are the optimum conditions, rather than the traditional master plan, star architect drawing a few circles, drawing a few crosses, drawing something, drawing a dragon, and that's the new master plan in China.
Can I ask a question? Going back to that previous question and what you said, like architecture is like moving towards a network between architects and structural engineers that makes a difference from the traditional atelier where the architect was in charge of design, and then you put the design and you go to the structural engineer's office and see if that can be built or not. How much, in a sense, how much percentage of the design was involved on the Watercube structural engineering in relationship to architectural design?
Well, firstly, when we talk about the old architects like Andrea Palladio, originally the architect was sort of the mastermind in charge of everything and had a knowledge of everything, but now complexity of problems has increased dramatically, and therefore I guess it's just unreasonable as a single person to think you can be on top of all these issues. With this particular work, I strongly believe that it's a network of a lot of people, and every single one of this network has its contribution to it. I don't like to put a percentage into it. It depends on who you talk to. It's like the Elvis Presley convention. I've heard talks of the structural engineer in Sydney where he basically put the finished building as the first image and said that was the sketch before the architects came into play. And maybe when I talk, it sounds like the engineers weren't even there. And the truth is, all of us, a team of probably 20 people, contributed to a design that emerged and became this building. And everything else is just part of the truth.
Maybe one more tricky question.
Okay.
How aware are you of the materials which are you using for the building are produced, or how ecologically efficient the material you are using are? Because of course you are talking about how efficient they are, steel dimensions and so on. If you can go outside of the box.
Yeah, well, I can't give you the exact figures of that, but I understand that materials have an embedded energy. If a material is 1% of a traditional material, and if the traditional material has to be manufactured, transported, lifted into place, and has to be replaced because it doesn't last as long, then it's highly likely that the 1% material has a better energy, total embodied energy. It's probably not 1%, of the embodied energy of glass, but maybe it's 30%. So yes, it's relevant to ask that question, and that's again something that when you design a city, that should be one of the parameters put into your computer system. Good questions, yes.